Welcome to the Curious Machine. Today we're doing a deep dive into infinity. And not just the idea of things being really, really big. We're talking about a concept that kind of challenges how we think about numbers, the universe, even motion itself. We've got some fascinating ideas lined up to explore why infinity isn't just a huge number, but something, well, something fundamentally different.
That's right. It's a word we use pretty loosely. Infinite. But in math and physics, it has these very specific, sometimes quite surprising meanings. So our goal today is maybe to cut through some of those common myths and show you where the really interesting insights are, from ancient puzzles right up to modern science.
Okay, let's unpack this then. When we say infinite, what are we really talking about? Is it just like a number that's too big to count, keep counting forever?
Well, the first surprising thing is infinity isn't actually a number at all, not in the way that 5 or a billion is a number. It's really a concept. Think about the counting numbers, 1, 2, 3, and so on. You can always add one more, right? No matter how high you go. That never-ending quality, that potential to always go further, that's the essence of infinity as a concept. It describes endlessness itself.
Okay, so if it's a concept of endlessness, what does that imply about the size of infinity? Like if you have all the positive counting numbers, and then maybe you add 0, or all the negative numbers too, does that make infinity bigger?
That's a great question. It gets into something called cardinality, which is basically how mathematicians compare the sizes of sets, even infinite ones. And here's where it gets weird. The infinity of just the positive counting numbers. It's considered the same size as the infinity of all whole numbers, positives, negatives, and 0 included.
Wait, really? How can that be? You've added infinitely many more numbers.
I know, it feels totally wrong, doesn't it? But mathematically, if you can pair up every item in one set with exactly one item in another set without any leftovers, they have the same cardinality. And you can do that pairing between the positive numbers and all whole numbers. We call this size a left zero. It's the smallest type of infinity in math.
Oh, left 0. Okay.
And get this, even the infinite number of fractions between, say, 0 and, like 1/2, 3/4, 7/8, that set also has the size of left 0.
Wow. Okay, that's counterintuitive. So it's not about just adding more things. It's about whether you can kind of list them out in principle.
Exactly. It's about whether the set is countably infinite. Can you create a mapping, a one-to-one correspondence with the counting numbers? If yes, it's a left 0.
Okay, my mind is slightly bent already. So if this is a mathematical concept, how does it connect to the physical world? Do we actually find true infinities out there or just things that are incredibly big?
That's a really crucial distinction. Often in physics, when the term infinity pops up, it's more like a shorthand. It might mean something is so large or so small that it's beyond our current ability to measure or properly model, rather than being truly mathematically infinite.
Can you give an example?
Sure, think about the surface of the Earth. You could, in theory, travel across it forever without hitting an edge, right? It feels unlimited in that sense.
Yeah, you just keep going around.
Right, unlimited movement. But the actual surface area, it's definitely finite, about 510 million square kilometers. So unlimited isn't the same as infinite in size.
I see. So unlimited path, but finite area. Where else does this difference show up in physics?
Well, mathematical models often use infinity to simplify really complex situations. It's a tool. Like if you calculate the theoretical force between two electrons, the basic math might suggest the force becomes infinite if they get infinitely close together. But in reality, when we actually measure things, or apply more complex theories like quantum mechanics, we find the forces get very large, but they don't actually hit true infinity. The model breaks down or needs refinement at that point.
So why use infinity in the theories at all if it doesn't perfectly match reality? Seems like it could be misleading.
It's because theories and models are fundamentally approximations. They simplify the messy reality to make calculations manageable and predictions possible. Think about drawing a line with a pencil. Mathematically, you could say that line contains an infinite number of points, 0 dimension points. But physically, that pencil line is made of a finite, though huge, number of carbon atoms. Remove the atoms, the line's gone. Our models often assume space is perfectly smooth and infinitely divisible, but maybe the universe itself has a fundamental graininess, like pixels on a screen. That's an incredibly tiny scale. Space-time might not be continuous.
Right, so the math assumes smoothness, but reality might be chunky at the bottom level.
Exactly. It often comes down to the limits of our measurements and the assumptions in our models. That's why some philosophers talk about the unreasonable effectiveness of mathematics. In physics, it works incredibly well even with these infinite idealizations, but maybe less so in biology or sociology, where things are far more complex and less easily idealized.
This idea of infinity being problematic,
Yeah.
it's not new, right? This sounds like it connects to some really old philosophical puzzles. Zeno.
Ah, yes, Zeno of Elea, an ancient Greek philosopher around the 5th century BC. His whole goal was actually to defend his teacher Parmenides, who argued that reality is fundamentally unchanging and motion is just an illusion.
Motion is an illusion. That's a bold claim. How did Zeno argue that?
He used this clever technique called reductio ad absurdum, basically. Assume the thing you want to disprove, in this case motion, is real, and then show that this assumption leads to logical contradictions, absurdities.
Okay, give me one of these absurdities.
The most famous is probably the dichotomy paradox. Imagine you want to walk to the end of a path. Zeno says, before you can reach the end, you have to reach the halfway point.
Makes sense.
But before you can reach the halfway point, you have to reach the quarter-way point.
Uh-huh.
And before that, the eighth-way point, and so on, infinitely dividing the distance. So Zeno argues you have to complete an infinite number of smaller and smaller tasks before you can even start moving, which means, logically, you can never start. Motion is impossible.
Whoa. Okay, that does sound like a problem if you think about it that way. What about Achilles and the tortoise? Is that similar?
Very similar logic. Achilles, the super-fast runner, gives a slow tortoise a head start in a race.
Right.
Zeno argues Achilles can never overtake the tortoise, because by the time Achilles reaches the tortoise's starting point,
The tortoise has moved a little bit further.
exactly, so now Achilles has to cover that new distance. But by the time he does that, the tortoise has moved forward again, a tiny bit more.
And that keeps happening forever.
According to Zeno, yes. There's always a small, ever-decreasing gap. Achilles gets infinitely close, but never actually passes. Again, an infinite number of steps seem required.
So the core idea for Zeno in both of these is completing an infinite number of actions in a finite amount of time is impossible.
Precisely. He also had the arrow paradox, which is a bit different. It looks at time. He argued that at any single instant in time, an arrow in flight must be occupying a space exactly its own size. If it's occupying that specific space, it must be at rest in that instant. And since time is just made up of these instants, and in every instant the arrow is at rest, Zeno concluded the arrow isn't moving at all. Motion is an illusion created by stitching together moments of rest.
Okay, these are genuine brain teasers. Obviously, we experience motion, we walk, things fly. So how are these paradoxes actually resolved? Did anyone just walk past Zeno to prove him wrong?
Well, there's a story about the philosopher Diogenes the Cynic doing just that. He supposedly heard Zeno's arguments, stood up, and simply walked away without saying a word. A very practical refutation.
I like that. But okay, logically, what was the flaw in Zeno's arguments? What did other philosophers say back then?
Aristotle, for example, tackled it quite directly. He argued that while the distance might be infinitely divisible in theory, the time taken to cross those smaller distances also gets proportionally smaller and smaller. He also made a key point that time isn't actually composed of indivisible instants, just like a line isn't composed of indivisible points. He saw motion as a continuous whole, not a series of static snapshots.
Okay, that makes intuitive sense. But how does modern math and physics handle it? Because these paradoxes rely on this idea of summing up infinite little bits.
Modern calculus is really the key. It gives us the tools to deal with infinite series rigorously. Remember the dichotomy paradox distances?
Yeah.
Half, then a quarter, then an eighth, and so on. 1/2 plus 1/4 plus 1/8 plus.
Yeah, that infinite sum.
Calculus shows us that this specific infinite sum converges. It adds up to a finite value. In this case, it adds up exactly to 1.
It adds up to 1, even though there are infinite terms.
Yes. Think of it visually. Take a line segment of length 1. Cut off half, 12. Then cut off half of what's left, 14. Then half again, 18. You keep adding pieces, making an infinite number of cuts, but the total length of the pieces you've cut off gets closer and closer to and ultimately equals 1. So mathematically, you can complete an infinite number of tasks if those tasks get appropriately smaller, faster. Calculus provides the proof. If S is the sum, then 2S equals 1 plus 12 plus 14, which is 1 plus S. So 2S, 1 plus S, which means S must equal 1.
Okay, the math checks out. But what's the physical insight there? Is it just about the numbers, or is there something more fundamental about motion?
It's more fundamental. Zeno's error, from a physics perspective, was focusing only on the infinite divisibility of space or distance, and sort of ignoring time and speed. Modern physics, starting really with Newton, treats motion as continuous. An object moving has a velocity, a speed, and direction. It's not just a jump from point to point. If you're moving at a constant speed, you cover distance continuously over time. You don't need to complete an infinite checklist of points to cross. The process itself is continuous. So considering speed resolves the paradox physically.
So calculus handles the infinite sum and physics handles the continuous nature of motion. Seems pretty well solved. Yet, you mentioned philosophers still find Zeno interesting.
They do. Some argue that, okay, math shows how motion happens, the sum converges, but maybe it doesn't fully address the deep metaphysical questions Zeno raised about what space, time, and change fundamentally are.
Like what?
Well, Bertrand Russell proposed the at theory, which basically says motion just is being at different places at different times. That's it. No need to explain the flow. Others, like Henri Bergson, argue that while we can divide the path an object takes infinitely, the actual act of moving is a single, indivisible flow, something our intellect struggles to grasp.
Huh. And didn't you mention something about quantum physics?
Yes, bizarrely. There's something called the Quantum Zeno Effect. It turns out that if you continuously observe or measure a quantum system, you can actually prevent it from changing or decaying.
You can freeze it just by watching it.
In a sense, yes. Frequent observation resets its evolution. It's eerily reminiscent of Zeno's arrow paradox, the idea that observing the arrow at an instant freezes it. Reality is definitely stranger than Zeno might have imagined.
That is truly weird. Okay, so we've dealt with basic infinities, but you hinted earlier and we touched on LF0. Are there really different kinds of infinity? Bigger ones? How does that even work?
Right, let's circle back to that. This goes deep into pure mathematics, particularly the work of Georg Cantor. We established LF0 is the size, the cardinality of the counting numbers, 1, 2, 3, and also fractions. It's countable infinity. Cantor proved that there are infinities that are fundamentally larger than LF0, infinities whose elements cannot be put into a one-to-one correspondence with the counting numbers.
How? What kind of numbers are those?
The most famous example is the set of all real numbers. That includes all the whole numbers, all the fractions, but also all the irrational numbers, like pi or the square root of two numbers whose decimals go on forever without repeating. Cantor showed, using a really clever argument called the diagonal proof, that you simply cannot make a complete list pairing every real number with a counting number. There will always be real numbers left out, no matter how you try to list them.
So the infinity of real numbers is bigger than the infinity of counting numbers.
Yes. A provably larger infinity, we often call as cardinality C for continuum, or sometimes LF1, assuming something called the continuum hypothesis. It's an uncountable infinity.
Mind blown. Okay, a bigger infinity. But then, what about those ordinal numbers you mentioned briefly? Is that yet another layer?
It is another layer, yes. Cardinal numbers like LF0, LF1 measure the size or how many elements are in a set. Ordinal numbers deal with the concept of order or sequence, especially when dealing with infinite sets.
Order. How does that apply to infinity?
Imagine you have your infinite list of counting numbers, 1, 2, 3, going on forever. That whole sequence in that order can be represented by the first infinite ordinal number called omega.
Okay, omega represents the whole infinite list.
Now imagine you finish that entire infinite sequence, and then you start another step after all of them. That would be omega plus 1, well plus 1, then omega plus 2, and so on. You can even imagine completing that infinite sequence, and that would be omega times 2.
Well, wait, you can do arithmetic with these infinite sequence markers.
You can. Ordinal arithmetic allows mathematicians to define and work with well-ordered sequences that go far beyond just LF0 in complexity. You can have infinities that come after other infinities in a specific order.
So it's not just about the size, but the structure and sequencing of these endless processes.
Exactly. It shows how mathematics can build these incredible conceptual structures that go way beyond anything we can directly observe in the physical universe. It's a language capable of exploring concepts far richer than just counting physical objects.
Wow. What an incredible journey from thinking infinity is just really big to, well, different sizes and even ordered sequences of endlessness. We started seeing infinity not as a number, but this concept of no end.
Uh-huh. And we saw how physics uses it often as a useful approximation, a stand-in for beyond our scale rather than a literal reality sometimes.
Right, and how tools like calculus gave us a way to handle those infinite sums that seem so paradoxical to someone like Zeno.
Yeah, resolving those ancient puzzles by bringing in concepts like speed, time, and mathematical limits. It really shows how our understanding evolves, doesn't it? From Aristotle to Newton to modern calculus and even quantum mechanics.
It really does, and I guess this whole exploration of infinity underscores that our knowledge, our theories, they're powerful tools for understanding, But maybe they don't capture the universe absolutely perfectly.
That's a great takeaway. They're incredibly useful approximations, constantly getting refined, helping us grasp more and more of this complex reality.
It leaves you wondering, though, if mathematics can dream up these different sizes of infinity, these ordered infinities like omega, concepts that seem to exist purely in logic beyond physical reality. What other incredible ideas, what other structures of thought are still out there just waiting for us to discover or invent them?
Thank you very much for sharing this enjoyable conversation with us. Until we meet again tomorrow with a brand new topic, take very good care of yourselves. Goodbye.